structure have the same crystal structure, generally they will have a different lattice constant. So the relative position of the atoms will be different. So if we want to embed this structure inside of the dot, somehow you can understand that we have to compress it to have it here. And this will generate this intrinsic local strain here, this epsilon is 0. So, and when the dot is inside of the matrix, we will try to get it to reach the equilibrium. And because of this, we will have this mechanical field, this strain field that we want to calculate. And then apart from this, there is another aspect, and which is the electrical part. Because we know that under some applied stress, the lot of material, the one we are interested in, generates an electric field. This is called the piezoelectric effect, which at least as a first order would be considered proportionate to strain. This is also to the vice versa, because if we apply to this material an electric potential, we will see a stress. So there are different models for this kind of electromechanical field, and in the following I will mainly focus on two of these models, basically the continuum model, and also I will talk to you a little bit about the valence force field model, which is an atomistic one. So let's start to introduce the first structure, which is the bullseye quantum dot. These crystals, they grow along the z-axis and also exhibit a spontaneous polarization along this direction, which means that apart from the piezoelectric effects, we also have a spontaneous polarization inside the material. You have the crystal structure, you can see the two different atoms that constitute this structure on the different plane. It's quite interesting if you consider this in the XY plane, since we can see this very nice hexagonal symmetry, and we have the z plane which is perpendicular to this, and this is the plane of the growth and also the plane of the spontaneous polarization. And this is interesting because we can consider it at least as first order as also cylindrical symmetry, and we will use this a lot in the following. So, I want to present, this is the, let's start to introduce the continuum model, and we start just with a question, not much more. So we will start from the constitutive relations for the continuum model. Here we have the stress tensor and the electric displacement, and they are related to the strain tensor and to the electric field by the elastic constant and the piezoelectric constant and permittivity, and here also we have the spontaneous polarization. This is a very general relation for every kind of crystal. In the case of the bullseye structure, we have a few linear independent constants, and these are the ones that we have. And using this constant and the relationship, we can write down the governing equation for the electromechanical field. So basically, the Maxwell and the Navier-Stokes equation. So basically, what we have is a set of four coupled differential equations that we want to solve to calculate the electromechanical field. Now, at this point, I would like to make a clarification, because sometimes when we talk about the continuum model, it's not completely clear. When we talk about continuum model, we have to consider usually there are two different versions of the model. We have the so-called fully coupled continuum model and the so-called semi-coupled continuum model. Which is the difference? When we talk about fully coupled continuum model, basically we have this set of four differential equations and we solve them at the same time. So we have a solution complete for the mechanical and the electric part at the same time. When we talk about semi-coupled model, basically what we do, we disregard the electric part of the first step. So for example here in this relationship we put this equal to 0 and we only have this part, and this basically is the Hooke law for the crystal. And then we solve only the part for the mechanical part of the equation, and then in the second step we use Poisson-Maxwell equation to solve for the electric field. Obviously to solve the semi-coupled is also less demanding from a computational point of view, but we will see in a while that we have some difference. An important point concerning this equation for the bullseye structure is that they are invariant under rotation around the z-axis, and this is for the reason for that symmetry that I showed you before. And this is very important because we use this symmetry as the first step to develop a two-dimensional model in cylindrical coordinates for a gallium nitride, aluminum nitride quantum dot. So we start with this two-dimensional model, use a very simple structure for the quantum dot, basically a cylindrical quantum dot, and we develop this two-dimensional model on the RZ plane. Here you have the dot, basically this is half of the cylinder because we consider the rotation, with a radius of 6 nanometers and height of 3 nanometers inside, and this is the method in which it is embedded. So we started with this model, two-dimensional model, because of this invariance under rotation. Here we have the first results for the strain distribution. Here I'm plotting the epsilon ZZ strain distribution, but the results are similar also for the other quantity. And here we have the different case, including or not some effects. I would like mainly to focus on case number 1, which is the blue line down here, with all the effects. So basically this is the fully coupled model where we included all the effects. And basically to look at the case number 4, which is the green one here up, where we only include the lattice mismatch. So basically this you can consider as the semi-coupled. And you can see that there is a quite notable difference using the 2D model for this structure. And also we have similar results for the other quantity for the other strain field. This is the two-dimensional model, and now obviously the second step is to compare it with a complete three-dimensional model. And this is what we did, so we developed a fully coupled three-dimensional model, and we compare the results. Again, here I'm plotting epsilon ZZ. So on the left here, you have the model, the two-dimensional model in the RZ plane. So it is out of the cylinder. And here you have just a slice. Basically here is in the middle of a completely three-dimensional cylinder. Just to have the same plane here, obviously this is the double because we consider all out of the cylinder. And you can see that not only if you consider the qualitative point of view of the field, but even if you look at the maximum and minimum value of the strain inside and just outside of the dot, you can see that we have both the qualitative and quantitative very good agreement between the two models. And this was quite expected because of the invariance of the model itself. And also for the other quantity we have such good agreement actually. And using the three-dimensional model, the fully coupled, it's also possible to have a look to the lattice field, and here you have the absolute value of the lattice field, and you can clearly see that it is cylindrical symmetric as expected from the equation. So this was the first two steps, and then the following step was to go into something more complex, and also we introduced another model. So we started to do something in the atomistic field, and we developed our sitting-like model for a good-sized quantum dot heterostructure. Here the approach is completely different than the consumer model. We have the expression of the free elastic energy here, and you can see that this is given as completely different because here we have a sum over all the atoms here. This model is a nearest neighbor model, since the sum here inside of the bracket are sum on the nearest neighbor atom. D and R are the bulk, so basically are the distance of the pure material, D, and R is actually the distance of the atoms in the quantum dot. So basically, D will be the quantity we are going to calculate actually in this kind of model. Theta is the unrelated tetrahedral bond length, and alpha and beta are empirical material-dependent elastic parameters. There are a couple of things to be underlined about this model. Okay, first of all, this constant here could be related to the elastic constants in the continuum model. And since now I'm going to present you some comparison, basically what we did for this comparison, we used this relationship. So we calculate the elastic constant using these alpha and beta parameters, so to be sure to compare apple and apple. Then the approach of the model, as I said, is completely different. Basically, in this model, we have to minimize this expression of the free elastic energy, and what we actually have in the end are the real position of the atoms in the quantum dot. And then if we want to calculate the strain and stress and all that other quantity, we have to interpolate this atom position to have this quantity. So we don't have them directly. A last point is that in this model we don't have the piezoelectric effects directly. It's not included in the model. So if we want to calculate the electric part, we have to do it in the same couple. We have to calculate later using the strain and the stress field that we have interpolated. So what we did a comparison. We did a comparison between the two previous consumer models, so basically the semi-coupled and the fully coupled model. We did this atomistic balance for field. And also we considered some implication for the band structure, and we did this for a more realistic structure in this case. We consider some structure from experimental evidence. Basically this is an hexagonal pyramid. Here you can see we also include a welding layer in the structure for the strain calculation. Here we have the welding layer, we have the parameters, so the height of the dot, and this two distance dt between these 2 points and dt here. And we applied these three models of strain to three different dots with different dimensions. We use the same welding layer, but we changed a little bit, we play around with the other parameters to have different volume and aspect ratio. Here I'm going to